Emeryville.
Close by. Are you guys back in the office?
Mostly.
Okay.
I mean, a lot of things can be done from home, but a lot of things with real robots cannot be done
true.
from home
You have to have
either.
it.
So yeah, kind of need to run real experiments a lot of the time.
I'm
Yeah, and these industrial robots, you can't just put them in somebody's home. They're just a little too big and powerful.
How big is your robo? Like, is there a warehouse or something, or like some sort of what is it called? A lab?
Well, our office has a lot of robots. Yeah, I mean, I think at this point, close to half of our office footprint is robots. So yeah.
Wow. So the engineers are interspersed between the robots, or out in a different like room.
Well, I mean, it's actually it's one big space, so it's good because you're always aware that we're working with robots. You can never forget about it.
Wow, that's pretty
but
cool.
There's still like a zone with robots and a zone with people. I mean, it keeps it. I mean, the robots do make a good amount of noise. It turns out.
I see.
Like if you have a robot with suction cup, which is quite common for many applications. Suction cups are, I wouldn't say they're super noisy, but they do generate a decent amount of noise. So it's nice to be not right next to it at all times.
So I guess it feels like a factory space. That's really cool.
Yeah.
So hey everyone, thank you for joining. We're going to be starting in 2 to 3 minutes.
How about you, Bindu? Are you located in San Francisco or?
San Francisco, yes. And we're, we're all software. We're all fully remote at the moment. And we started as a San Francisco only company. We are now, I think, in 6 locations.
Got it.
And the most interesting one has been Athens. We just had someone join from Greece, and I was never a believer in remote work, and now I've become religious about remote work.
Oh, that's so interesting. I personally think, it depends a bit on what you're building with robots. I think it doesn't
that's
really
not possible.
work.
Yeah,
but
I agree.
If it's all software only, I think, it really depends on the type of people, honestly. And I think it's nice to have some companies be remote, some companies be non-remote, and different people can really, find the culture
whatever works for them.
Yeah.
No, absolutely. Okay, I guess maybe we should get started. Well, thank you, everyone. I know you guys are dialing in from various different places, so thanks for coming, especially the ones who are coming in from other parts of the world. I see Argentina, Canada, India, Pakistan, so fantastic. Let's get started. Hey, my name is Bindu Reddy. For those of you who don't know me, I'm the CEO, co-founder of Abacus.ai. I think a lot of you have probably come to one of our events in the past. So if you are coming back, welcome back. If you're new to one of our events, thank you for coming. State of the Art is a conference which has a handful of sessions. We hope to talk to kind of thought leaders in the industry and in academia, and talk about some of the interesting kind of the topic du jour in some ways with various different people. Today, just to kick us off, we have none other than Peter Abil. I'm super excited to have him. I got to know about Peter Abil the first time when I actually got interested in how deep learning can do multiple different tasks. He, along with another person, Sergey Levine from Berkeley, as probably some of you know, wrote this seminal paper around model-agnostic meta-learning. So, Peter, welcome.
Thanks for having me, Bindu, and hello, everyone. Thanks for joining.
That's great. Okay, so a little bit more of an intro to Peter. For those of you who don't know him, he's a professor of electrical engineering and computer science at Cal. He's also the director of the Berkeley Robo Learning Lab and the co-director of Berkeley AI Research. He's also found time to actually start a company, which is a pretty interesting, innovative company in the space called Covariant AI. I'm sure he'll tell us a lot about his company as well. Peter, let's kick us off with telling us a little bit about how you decided to choose this career. I know you wanted to like kind of drop out after your master's, but you chose to stay on and do a PhD. Peter also happens to be the first PhD student coming out of Andrew Ng's lab. So tell us more about what got you here.
Yeah, so actually, I grew up in Belgium, and towards the end of my undergraduate in Belgium, of course, as anybody, when you're about to finish your undergrad, you got to find out what you're going to do next in your life. And for me, it became pretty clear that artificial intelligence is what I wanted to do. That to me just seemed like the most interesting possible topic. I thought other topics were very interesting too, like neuroscience, but it just felt like neuroscience was so hard to make progress on, and AI seemed just like more amenable to making progress. And so I thought AI, the combination of amenability to progress and how interesting it is, that's what I want to do. And so I started looking around, and I found that, at least at the time, there wasn't so much going on in AI in Europe. As I started looking around, I saw, the places where it was really happening at the time, and luckily it's drastically expanded since. But at the time, it really came down largely to just a handful of places in the US. And so I was fortunate enough to get to do my master's at one of those places at Stanford. And so I did my master's there working with actually Daphne Kohler, who was my master's advisor, who has had quite the illustrious career and currently is working on AI for drug discovery. And towards the end of my master's, when I left Belgium, I thought I'm going to do my master's. I'm going to learn a lot of things about AI, and then I'm going to come back to Belgium, do my PhD in AI here, because I'll have seen all the different things, and then I'll have the context to do it here. But after I had been at Stanford for even just a couple months, it became pretty clear that just the energy, the dynamic, the kind of people present there that work in AI was just a different world. And it was just very clear that if I were to go back, there's no way I could achieve the same things. Like it's just the environment at Stanford would be just so much better to achieve bigger things in AI than if I were to go back. And then I had this really lucky coincidence, because as I transitioned from master's to PhD, Andrew Ng just finished his PhD at Berkeley, and he joined Stanford as a professor. And so, I mean, this is just a fresh professor. You might think like, why would you work with a fresh professor, a very little experience? But I knew from all the professors at Stanford and other places that I had seen interact with Andrew, talk about Andrew was the next big thing. It was just like he was, the most important person graduating with a PhD in AI in a long time. And I thought, well, this is going to be amazing. This is clearly who everybody thinks is the big next person in AI. And I can see them build their lab from zero to, it's just, I think nobody could imagine how everything he would be doing. It's absolutely phenomenal. But to me, that was just so interesting to get the opportunity to work with him from day one. First day he arrived at Stanford, I could start working with him. And actually in the first year, there was only 2 or 3 students working with him. So actually we could get time with him anytime we wanted to chat with him about something. It was just absolutely amazing.
That's great. Fantastic. I mean, it feels like you had an eye for picking the right things all the while, from Stanford to Andrew to AGI. Wonderful, wonderful. Okay, so for those of you who don't know, Peter actually was at OpenAI. I mean, everybody is always curious about OpenAI for so many reasons, as you probably know. So tell us a little bit about like the inside story there. Like, what made you go there? What made you then decide to leave and then join and then start Covariant?
Yeah, so to connect the dots here a little bit, during my PhD at Stanford with Andrew, it was a time where I would say the core of machine learning wasn't making as much progress as it was making today. And so most people working in machine learning, including myself, would work on a combination of machine learning with something else. So Andrew and I together, we worked on machine learning in the context of robotics, combining machine learning with state-of-the-art advanced control techniques. In our case, we applied it to helicopter flight, to do extreme helicopter acrobatics. But that was kind of the style of work we're doing at that time. I think around, and that was quite general. That work is also what got me the professorship at Berkeley, where I started a robot learning lab, which in the early days was really all about a combination of what can machine learning enable in robotics in combination with existing robotics techniques to together achieve something that neither can do alone. But I would say around 2012, there was a real shift in the field. And for some people, that's maybe even before they got started in the field. But for me, that feels like quite into my career. All of a sudden, 2012, a big shift. There was a big ImageNet moment. Jeff Hinton and his students at Toronto showed that, hey, all what people have been doing in computer vision, which was also combining computer vision expertise with machine learning, can actually be superseded by pure machine learning, a new type of machine learning, deep learning, training very large neural networks. And the idea and the reality was that with deep neural networks, the data can speak for itself. You don't code things in by hand. The data tells you what it is. And if you have enough data and enough compute to process the data, you set up a large enough neural network the right way. And back then that was hard to do, very hard to do. I mean, nobody could do it except for Jeff and his students at that time, of course. Then they shared how they did it and so forth. I think that was a real tidal shift for me, at least, in terms of, okay, it seems like there is an opportunity here to really advance the core of machine learning, specifically deep learning, to take it to a whole other level. And that is very different from saying, what can we do by combining existing machine learning and existing optimal control and so forth to get new results. And so that was the big first shift for me, 2012. And in my lab at Berkeley, we shifted to essentially revisiting reinforcement learning. We had worked on reinforcement learning a lot before. We'd actually been pretty quiet on it in the last couple of years leading up to 2012. But then we're like, okay, with these deep neural networks, maybe that allows us to revisit reinforcement learning and get it really right, or more right than we could before. And so that's, of course, the field of deep reinforcement learning, which at the time, DeepMind in London was working on very hard, as well as my lab at Berkeley with Sergey Levin, who you mentioned, John Schulman, Chelsea Finn, Rocky Dwan, and so forth. And so there was these two relatively small groups, my lab at Berkeley and then DeepMind, which was small at the time, obviously big now and so forth. But at the time, it was 10, 20 people. And there was these two places where we're both thinking we can actually get deep reinforcement learning to do things that were not possible before we understood maybe how to get deep learning to work. And so what happened from there is that there was this progression where there was these two places where at DeepMind largely focused on games, at Berkeley largely focused on robotics to get agents to learn from their own trial and error. And that progression led in some sense to it was really fun because it was just like very rapid progress compared to anything that was happening before. And the same thing was, of course, happening in computer vision, natural language processing. There was this, real acceleration in progress across many domains. And so to your question about OpenAI, of course, so what happened is at the time, DeepMind had their big results, first Atari in 2013, AlphaGo in 2015. And so at the time, there was some talk about, maybe a new lab should be started in Silicon Valley.
Google, right?
Say it again?
I said, which is not Google.
not Google, yeah, a new lab that is really focused on making sure as AI is progressing that it's for the good of the world. And of course, this turned into OpenAI. But before it even existed, the founders of OpenAI were talking with each other about what is it that we need to do, how to make sure AI is going to be for good if it's going to be so powerful. And this, of course, was Greg Brockman, who was the CTO of Stripe at the time, left Stripe to do this. Ilya Sutskever, who was one of the students of Jeff on the original result and many of the big results since. He was at Google at the time. Sam Altman, the president of Y Combinator at the time. Elon Musk, which, need no introduction. I mean, that was the leadership in some sense, but from the early days, they said, okay, we need to somehow recruit experts in this space. And today there are more experts. Still, it's scarce, but back then the number of experts was very small because deep learning was so new, and there was only a few labs in the world where PhD students had been working on this. And so one of the things they did, they came to Berkeley, right? And they said, okay, well, they want to understand, what's going on at Berkeley. Who are the people doing interesting work and so forth. And one conversation leads to the other. But actually, one of my students, John Schulman, who was the main driving force between most of the deep reinforcement learning work in my lab, he decided to become a co-founder of OpenAI as he was about to graduate. John, and then same thing, Andre Karpathy from Stanford, Wojciech Zaremba from NYU, Dirk Kingma from Amsterdam. And so those were the founding researchers. And John being my student, and we've been working together for 5 years at that point. I mean, he was like, he told me about it. He says, this is what's going to happen. We're going to found this new company. This is the mission. And we're building this team that's really an amazing team, And, he said essentially, look, probably would be really fun for you to spend some time here because this is going to be such a dynamic, creative place. And I went to visit a couple of times and I was like, yeah, John, you're right. I mean, I cannot imagine, like any time I visited in those early days before it was even, officially announced, even like anytime I visited, I was just like, okay, this place is just the amount of creative energy here. It's hard to imagine spending my time anywhere else. Like this is where the best ideas are being created. And I just want to be part of this. And, there was just a really good fit between my expertise and what they were going for. So from there, just, spent 2 years there.
Oh, fantastic. I mean, that is a really great story. It almost reminds me, this might be an exaggeration, but I don't think so. It's like the founding of the country or something, when all the founders of the country got together. Like, you guys are all very famous, right? And then imagine all of them coming together. And no wonder OpenAI is what it is today. But that sounds super exciting. And also, it also speaks to how kind of close-knit the community is, right? And how collaborative everybody is, which is fantastic. I find that that's one of the greatest things about what has happened over the last few years has been that companies even aren't like so closed. I mean, everything gets published. Things are like, things are actually much more collaborative. So tell us a little bit about, I at least have been very fascinated about the idea of actually models doing multiple different things at the same time. We over at Abacus do some deep learning, but all our models are very kind of task specific. We train a model for a particular task, and then that's what happens today, right? And everybody is thinking that, okay, in the future, sometime there is going to be this fantastic human-like AI. And humans, of course, can do multiple different things. I feel like you and a couple of others in the industry have been pioneers when it comes to this universal AI sort of thing. So tell us a little bit about that. What do you think about the technology today? How far are we from something like that? It could be that we're already there. So tell us more.
Yeah, I mean, I'm obviously fascinated by systems that are ever smarter and smarter and smarter. And I think as you look at the spectrum, you start from, especially if you think in the context of robotics, you start from robots that are pre-programmed to do a fixed set of motions, right? Or maybe pre-programmed to react to a certain sensory activation to then do a specific motion. From there, you can start introducing learning to have, I would say, specialist robots that know specific tasks really well, that now, let's say, can see. Yeah. And that's actually, I mean, that's a very recent thing. And, the vast majority of robots in the world doesn't have a camera, right? They are just blind robots. I would say probably 99% of the robots in the world are blind. They don't see, they just repeatedly do the same thing. And so it's super clever what people do to make that work, but it's very limiting. I mean, when you think about robots building cars, you're like, wow, that's amazing. I mean, they do amazing things, super precise, and so forth. But it's kind of pretty much, if you look at where the robots are, that's pretty much where they are. They're doing these repeated motions to build cars and electronics, and they don't really go anywhere else because they need to be able to see. And so that's the big new thing, robots that can see. But initially you could think about, well, a robot I can see to solve one specific task. But the real future, of course, is robots that are very general and more general. AI systems are very general that can pick up on a new task quickly and acquire that new skill almost instantly. Because to me, when I think about AI, I kind of think about two big things for my own motivation. One of them is just this fascination with, humans have this thing, this intelligence that is so flexible, so general. How is that possible? Can we understand that? And can we understand it by engineering something that's similar? And the other part, of course, is if we can do that, the impact is tremendous because it can come help out in so many different places.
Yeah.
And so when I think about, the gold standard of building AI should be something really, really flexible, even though many applications today, something specialist might just be the right thing to do because ultimately you're building an application to help somebody today, right? But research-wise, I think the generalist version of AI is the most exciting. And it's also most challenging because you somehow your system has to absorb a much wider range of things. It can't just absorb this one type of data, one type of concept and call it done. So yeah, I'm really excited about multitask learning, meta learning. And especially, as you see some of my recent papers, I'm really excited about starting with self-supervised or unsupervised learning on very open-ended data sets. In my case, it'd often be visual data sets because I think of robotics as a natural application, but you see similar work happening, of course, and it happened actually earlier in language, where, train on so much text out there, and actually OpenAI was the pioneer of this, train on so much text out there that you have this general base of knowledge, and then you can learn something else quickly. For me, the counterpart when I think about robotics, the future of robotics is you train on so much video that your robot, just by having been trained on so much video of what happens in the world, just starts understanding how the world works. Because the only way you can understand what's happening in those videos, if you're forced to predict possible futures, you have to understand that there are objects, the notion of objects. You have to understand that there is a 3D in the world and that things can get occluded, but then become visible again when they come out on the other side. You have to understand so many things about how the world works to be able to predict possible futures, that by forcing the neural net to do that, I believe, and we're seeing a lot of preliminary results for this, of course, even though I would say there is a home run result yet, like GPT-2 or 3 has been in language, right? I don't think there's a counterpart of that yet, but I think we see signs that, we're making progress towards having a video version of that, which in turn can really empower a lot of visual and then, for me, especially robotics applications from there.
Wow, that would be fascinating. A GPT-3 for video, and I have no doubt it's coming. Generally in terms of the science behind this, what is it telling you? Like you're obviously deep in this, and to me, I'm not obviously someone who's reading this, but not as deep as you are. It feels like things are collapsing, meaning like the pattern. The same kinds of technologies can be applied for language and video and so on. So it almost seems inevitable that we're going to have this GPT-3 for video, and that's going to be like very aha, right? How do you think about that?
I think it's really interesting the way you put that. It feels like things are collapsing. Of course, collapsing can have a negative connotation.
In a positive way, hopefully.
So I would maybe think of it like things are converging on the same kind of tools, which is a really good observation, right? And I think deep learning really started that, right? Back in 2012, the original versions of deep learning, of course, were not as converged as we are today. Back then, the deep learning for NLP was wildly different from the deep learning for vision and for speech, for reinforcement learning / robotics. It was all quite different. And now you're absolutely right. What we're seeing is that these new architectures, the transformer architectures, seem to be more general. And to me, that's super fascinating because there are these studies, right, of the human brain where a blind person, with most people, when you go from person to person, you can find that roughly the same region in the brain does the same things, right? And so roughly the same region for you and for me will do our visual processing. But then for a blind person, that region might end up repurposed to do other types of processing. And so that's a proof of concept in some ways that our brains, or at least the brains of the people that they observe this with, but likely it's true for other people too, that our brains are very flexible, right? And so to me, it's really exciting to see this happen with the transformer architectures, because what you see is a single architecture, and this might not be the final one. I'm not saying this is the final one, but we see that we are now we found an architecture, and obviously the original paper was out of Google. I'm not including myself into figuring that out, but as a community, we found an architecture that is really general, and it's fascinating that we've gotten to that stage, and who knows where it goes from here. But there's definitely this coming together of all the different fields, and actually, it also gives me a lot of confidence that we can actually combine a lot of things. If you think about, learning video prediction models to aid robotics, well, we can actually learn language prediction models to aid robotics, because at a higher level of abstraction, you maybe don't need the video. The video is to get the details right. If somebody says chop vegetables and then put them in the pot, that's the higher level recipe. That you can actually just get from language, as long as you also have some video somewhere that tells you what it means to chop vegetables or what it means to put them in the pot. But then once you have had enough of that video, you don't need to see every sequence of activities. Language is essentially the compressed version of that once you understand the visual motor part.
Wow. Okay. I'm sure lots of exciting things happening now. You run a company, Covariant, and I'm sure at Covariant you have what I'm going to call revenue pressure, at least a little bit. We've got to make some money, right? What about the practical applications today? I mean, I know the Covariant AI or the Covariant brain also, the intention there is to use things like deep RL or deep imitation learning. It seems like, so for someone like me starting a robotics company, I'd be like, okay, what can be applied today pragmatically in the world? That's probably very specialized, right? So how do you balance those two? And first of all, are you guys thinking, no, we're not going to do specialized learning. We're always going to think about something in the meta learning context or the generalized learning context?
Yeah, those are exactly the kind of questions we, of course, asked ourselves as we're getting going. So what happened is, in late 2017, for me, it became kind of clear that this was the right time to start transitioning all this research progress. Actually, in many domains, a lot of research progress in AI could be transitioned into applications, right? And it was a really good time to think about starting companies. Of course, I didn't want to start multiple, but it was a good time for people to think about starting companies, rather than just continue to stay focused on pure research at all times. And so to me, of course, having a long history and passion for robotics, to me, it was the right time to say, okay, this is the time where we can take all these recent advances in deep learning for robotics and start building applications that are completely different from the existing robotic automation that's out there. And so at the time, I actually sent a note to all my students. I said, hey, I think it's the right time to transition some of these things. Of course, keep inventing. We can't just transition. We need to kind of keep pushing forward. But the time is right to build on what's there and then push with an application in mind. And turns out 2 of my students replied to me. Rocky Dwan and Peter Chen, who ended up being co-founders of Covariant. Peter became the CEO and Rocky the CTO. And they said the 2 of us been talking about that among the 2 of us. Like we've been talking, okay, this seems the time to do it. So we're curious to compare notes. What do you think would be, the right way to build a company? What would make this, the thing that you want to do versus what we want to do? And it turns out we were just really well aligned. Maybe no surprise, because PhD students get to choose which professor they work with, and typically you work with a professor you have a natural alignment with, and so forth. But they replied, and I was super happy because they were just absolutely phenomenal PhD students. In fact, they were, in parallel to doing their PhD, they had been recruited into OpenAI Peter, before he even started his PhD, and Rocky, and a couple months into his PhD, back when OpenAI just had 10, 15 people, so it was just like top recruits across the world, in even the early days of their PhD. So absolutely phenomenal. I'm like, wow, that one, I think it's the right time. Two, I get this opportunity to do this with these two just best possible AI researchers that I can imagine working with. We just got to do this, right? And so when we started thinking about the questions you're talking about, right, Bindu, it's like, okay, building a company means thinking about bring it into the real world. And so the first question is, what does that mean to bring it into the real world? Bring robots into the world. What can it do? Like if you think about a general robot, it could do anything. Like if you had a purely general robot, like it could do any physical thing anywhere in the world. But we're not there. We're not there that we can deliver on that kind of capability. Nobody is, obviously. I mean, if anybody were, we would see the robots all around us. They'd be, loading, unloading our dishwashers. They'd be cleaning our houses. They'd be maintaining our yards. They'd be doing everything for us, right? So that's still the future. But we're thinking, okay, what can we do in the near future to build a business around? And so the first thing we did, actually, we said, let's just spend time investigating markets. And so in the first half year of Covariant, I met, together with Peter Chen, two of us together met with 200 companies.
Okay.
Listening to them, understanding if you could get a smart robot, so not a repeated motion robot, the kind of existing category of robotic automation, but a smart robot, one that can see, react to what's in front of them, do the right thing. What would you want that robot to do? And we talked with car manufacturers, hotel chains, farming, equipment companies, construction companies. We thought about home applications, like literally anything you can think of. We had conversations with the relevant people. And to us, it was very clear. After those conversations, logistics and warehousing is where there's the combination of people are asking for things that we think we can deliver, and they want it now, not in the future. It's not something where they're like, we'd love to get a demo set up in our innovation lab, and then we'd love to show it to our CEO and inspire our CEO. And they would be like, if you can deliver this, we want it now. And so that was a very different feel we got. Now, of course, everybody would say, if you can have a complete human level like robot, you can deliver it today. But they were asking for what seemed to us very advanced yet realistic things for us to deliver. And they wanted it sooner rather than later. And so to us, after 3 to 6 months of investigating the space, it was clear that's where we're going to go, at least as the first place. We always kept in mind, once we go to one place, if we do really well, we can, of course, expand, but we want to focus on one area first. And then very interestingly, the first thing we thought about, okay, we see all those facilities and e-commerce is growing so fast, and that's a big driver. And we're like, okay, we should probably do, let's say, returns processing. That seems pretty hard. Nobody else is going to come get anywhere close to being capable of doing that. And they'd say, yeah, if you can do that, that's great. But they'd also say, well, actually, if you could do pick and place, that's the first thing we need. And we'd be like, well, pick and place, it seems other companies that already existed are thinking about this. Why another company doing that? But then something really interesting happened at GTC in 2018. So 4 years ago, GTC is happening this week, actually, NVIDIA's GTC. Knapp was there. Knapp is a big warehouse automation company. They provide conveyors, robots that do the transport of things in the warehouse and storage and retrieval and optimized storage and so forth, right? And some of their engineers were there, and they came to me there after I gave a talk about progress in robot learning. And they said, if you can do all this, can you do pick and place? And I said, I think, yes, we could do pick and place, but there are other companies, we want to do something that other people are not doing yet.
Yeah.
And they said, they're trying to do it, but we've tried the solutions that exist on the market right now. And this might be a harder problem than you think. If you think you can actually do it at the reliability that's required to deploy in the real world, which is very high reliability, I mean, show us, and we want to partner with you because we can't find it anywhere. It's just not reliable enough. It's good enough to do demos. It's good enough to have a 30-second video.
Consistent. Yeah.
But it's just like self-driving. We've seen self-driving demos for 10 years longer, but seeing a 30-second, 5-minute even demo doesn't say anything about the viability. It says that, it's at least not really bad, but it doesn't mean it's viable. And so the same thing here. And that conversation really drove us into concluding that, okay, we should prove out reliable pick and place for any kind of item in a warehouse. Take it from one bin to another, or from a bin, scan into a shelf, or from a conveyor belt, scan onto another conveyor belt. But a very general solution to pick and place, that's what we need to focus on. And that's what we've been focused on. It turns out to be a very, very rich problem with so many applications in the real world if you can do it reliably. And so doing it reliably is really, when I think about, what makes Covariant unique, is the level of autonomy that we're able of achieving in pick and place. Like, we're capable of doing this at a level that is so high that it creates real value for our customers. And I'll admit, it took us longer than I thought it would. Like, we had a demo up and running pretty quickly, but we put 99.5% as the level you need to be at to call it viable in terms of autonomy. To get there, it took us a couple of years to get to that level. We had to do a lot of internal research that we don't share the details about because it's our secret sauce, that we know how to do this better than anybody else. And it's a hard problem. And it's so funny because a 3-year-old can do pick and place. But a 3-year-old cannot beat the world champion in Go. Yeah, but somehow the pick and place is so much harder because of the wide range of scenarios you end up encountering. Everything's always different items, different packaging, different situations. And you need to handle every version of this to create value.
Fascinating. I think the demo/research to the real world gap is a real one. It's a really big one, and it's very interesting because I think it applies in all areas of deep learning, right? All the way from something as simple as, like, say, I won't say simple because we do forecasting. It's actually quite hard. From something like forecasting to like what OpenAI is doing and what you guys are doing. Mm-hmm. So tell me a little bit about. So I think there are two approaches here that I've seen taken, right? And I don't intend for you to give away your secret sauce, but the question is, it feels like say someone like AV, like Waymo, is memorizing these nuances a bit. One of the biggest knocks that you see even with GPT-3 is everybody's like, oh, these are just like, memorization models. They memorize everything and therefore they see something again and, they just, spit that back to you, versus learning, right? Where you're like looking at enough scenarios, kind of in some ways deconstructing it maybe, and then therefore applying it to new scenarios, which potentially feels like how the human brain works. So what is that trade-off there? Do we think we're still kind of mostly memorizing, most of our models in the memorization world, or more kind of in the learning world, or beginning to move there?
I think that's actually a question I often end up seeing debates about. How much are deep learning models really learning versus memorizing? Obviously, there is some kind of learning, right? At a certain level, you can show it an image that it's never seen before,
right?
And it'll recognize what's in that image,
right?
But then at the same time, that image will be quite related to a set of images it's seen before, and so there is some kind of generalization for sure. But at the same time, the generalization that we're seeing with our current deep learning methods has not been at the level that humans generalize. And then often the question is, what does that even mean? Maybe humans just generalize so well because they have seen so much data in the past. And maybe we've seen it all ourselves too, or maybe not. And I think that's a pretty big open question there. But to bring it back to the practical reality that you're alluding to, at Covariant, when we think about how do we build what we call Covariant Brain, which is the software powering our robots, right? There is key philosophy that we've gone with from day one. And that has been that anything you hard code is likely going to come back to bite you. Because anytime you hard code something, you are making assumptions. And these assumptions could be violated. And then you could say, okay, if they're violated, then you just hard code some more things. But that's where things go kind of crazy in practice, because you have an if then else, if then else, if then else. And some people might say, oh, it's interpretable way of programming the robot. But actually, once you have 100 or 1,000 if then else statements, I don't think too many people can actually reliably gauge what this spaghetti code would be doing. And so from day one, we've said, look, we can't go down that path. Like, the way we can build long-term, most capable robot brains, is how we think of it, is by always being learning and data-driven. If something doesn't work today, we have to be able to fix it by collecting more data of that type, training our covariant brain, which is large neural networks, to absorb what's in that data. And now some people would, of course, say, hey, why are you throwing things out? Couldn't you, for some things, you just know what it's supposed to be? Well, if you know what it's supposed to be and you could hard code it, you can use that as a data generation engine, right? You can use the data and generation according to the process that you know,
and then learn
generate all that data. You learn from that data, you internalize that concept. But if then ever there's a violation of that concept, because pretty much, it's like, the good old school AI things, right? Like, birds can fly, right? But then you run into a bird that can't fly. What does that mean? Is a bird that lost their wings still a bird? Is a penguin a bird or not? It's just like, it gets complicated very, very quickly, right? But if you're data driven, you just have just a new type of data, you add it to your existing data, and your model internalizes it. So that's one big part of our philosophy. We need to be able to improve things with data and learning. A related part is that the hard thing with building AI for the physical world is the long tail. It's the fact that there is so many things that don't occur very often, but together, there's a lot of it. It's a big mass. It's a heavy tail, not just long, but it's also heavy. There's a lot of probability mass in it. And so what that means is that we believe strongly, and we've found this so far to be true, and I'm pretty confident it's going to be true forever pretty much, but that you want to train a single model for everything you do. You don't want to have a separate covariant brain for picking groceries and a separate covariant brain for picking electrical supplies and a separate covariant brain for picking maybe apparel, yet another covariant brain for picking, health and beauty items and so forth. You want a single brain. And in terms of things that a lot of people more naturally think about, let's say self-driving cars, it's the same thing in my mind as saying you don't want a separate system for highway driving versus city driving, because there's actually shared things. And by making it separate, you're splitting your data, you're cutting your ability to generalize drastically. It's by sharing all that, by having a single brain that has to be able to do everything. That sharing is actually, going back to what you asked about initially, Bindu, I think that sharing is what leads to the ability to generalize better. And so that's been our philosophy from day one. We still run with that. We'll keep running with that.
It's a hard philosophy to follow, but the right one, right? That's the trade-off. In the short run, it feels like, let's just split it. It's easier to build two models good at two different tasks. But in the long run, this is the right way to go.
And this goes back to your very initial question about multitask, right? This is multitask in some way, but we're saying, actually, we should consider it a single task. We shouldn't think of it as multitask, even though naturally you could maybe say it's multitask. But we say this is a single task if you want to do it maximally well. Even if all you care about is, let's say, health and beauty products, by also training your brain on all these other things, you become better at health and beauty products also.
Fantastic. I love your tenets, the philosophies, basically saying, hey, while we want to build for one particular problem or solution, we're building that in a very generalized way. We're not like kind of hard coding things. I totally agree with, I think across AI, all the companies, of course, ours is, I would say a little bit more kind of real worldy, meaning we're tackling simpler problems. Having said that, though, the same tenet applies to us as well. Like, don't do something which is very hard coded for a particular customer. Like, do it in a general way. I think that philosophy actually builds kind of like inherent intelligence, which is valuable for humanity. Right, just much more and sometimes bigger than the company itself. I think that's absolutely wonderful, fascinating. Tell us a little bit. I don't know how much time we have, but I'm really curious about imitation learning. So maybe a minute about that. Deep RL versus imitation. You think imitation learning hasn't? I mean, it seems like it's not as buzzy, for the lack of a better word, than RL is. What do you think about the future of imitation learning?
Yeah, when I think about RL and imitation learning, I think is just as important as reinforcement learning. Absolutely. If we think about the practical, I think the reason reinforcement learning gets more attention and more buzz is because it's more mind-boggling, right? In reinforcement learning, the agent learns from scratch. Initially, it's just struggling, and then over time, it figures things out on its own, and it's just beautiful to watch that in action. All of a sudden, the robot can walk or can get up, and so forth, right? But the truth is, reinforcement learning is not very sample efficient. The upside is that the robot or agent collect their own samples, but the downside is that it does require a lot of samples, right? So the beauty of imitation learning is that very often, by giving a few examples, a system can directly learn to imitate. And this could be in the context of robotics. This could be in the context of other things, like maybe a support agent that's having a dialogue and has seen past dialogues and matches the behavior in those past dialogues. And so one of the reasons I think you don't see as much about imitation learning in the research world is because I would say that I wouldn't say it's an easy thing, but it has less complexity than reinforcement learning. And so there is less maybe things to directly improve upon, right? So with reinforcement learning, there is, should you explore? Should you exploit? What's the best way to explore? How do you internalize all this information? Are you going to build an internal model of the world? Or are you just going to do model free? There's so many choices in reinforcement learning. Of course, there's a lot of connections between all the different algorithms. There's so many choices, and it's still so sample inefficient that it feels like there's so much room for improvement, right? On the other hand, in imitation learning, when I look at it, the methods are quite similar over the last 10 years because you're essentially doing supervised learning with a little bit of extra, typically because you need to do well on a rollout, not just on a one-off decision. But so there's less room for maybe innovation is maybe the way to think of it. Okay. But there's a shift in that. And so the way I see the shift is, one shift is how well can imitation learning do when you have massive pre-training? I think that's a really interesting question that we see more attention to now. You pre-train a lot of video, then you imitation learn on a few examples. What's the effect of the pre-training? And then related, can you find representations that can handle multitask imitation learning, or that can do few-shot imitation, quickly adapt to new demonstrations? So there are a few research directions, but in some sense, all of these also exist in reinforcement learning. Also in reinforcement learning, you can say, what is the effect of pre-training? What is multitask reinforcement learning? What is few-shot reinforcement learning? And the complexity is higher in RL. And so
therefore that's challenging and people are gravitating.
Yeah, I think in practice, you might see a lot more imitation learning than reinforcement learning, at least today. But in research, you're going to see more reinforcement learning research.
Okay, sounds great. I mean, we're almost on time. I guess there were a few questions. I think we can run over a little bit. I guess one of the questions we have was okay, do your robots use any, this is an easy one. Do your robots use any tactical feedback from an item in addition to video stream? Probably yes, but yeah.
Well, so one of the things that we noticed is that a surprisingly large amount of tasks in pick and place can be done with suction cups. Okay. Now, so suction cups know when they have a seal or don't have a seal. So that's one time. I mean, tactile is, of course, depending how generally you think about tactile, but that's a physical feedback mechanism. You can also install force torque sensors on essentially the connection point between the arm and the suction cup attachment. And so there is feedback like that. We don't use tactile feedback the way you might think of like human fingers, tactile feedback, that kind of level of sensation. That's not something that actually exists as a product. I mean, if it were to exist as a product, we'd probably be looking at it. But that's a really important current research direction, to build really good tactile sensing. And I hope it'll come into existence, and I think it'll open up a lot of new opportunities when it does.
Fantastic. Okay, one last question. What techniques would you recommend for debugging introspection for RL models? Deep learning models are always hard to debug. But anyway, for example, if the model works very well 98% of the time, but then performs terribly in 2% of the time, how do you find what's wrong?
Yeah, I think, it remains tricky, especially for RL models to debug them. There was actually a really nice tutorial that my former student and then co-founder of OpenAI, John Schulman, put up a while back, and it's called The Nuts and Bolts of Deep Reinforcement Learning. And he gave that talk a few times. I think once at NeurIPS, once at a deep learning day that I co-organized with Andrew Ng at the time. And I would recommend checking that out, because honestly, there's a lot to it. I think the 45-minute talk is actually the right answer to it. So try to find John Schulman, Nuts and Bolts of Deep Reinforcement Learning. And if you somehow can't find it, drop me an email and I can see if I can help you dig it out.
Well, wonderful. Thank you so much. That was a really fascinating talk. Thanks for coming to our, a little virtual event, and hopefully we'll see you again. Thank you so much, Peter.
Yeah, thank you for hosting, Bindu. And for everybody who's online live right now, I see there are more questions. I know the event will roll over to next thing, but I'm happy to stick around and type some answers to the questions that are in the Q&A. So I'll go do that right now. So your question will be answered.
Yes, there are quite a few questions. I figured we didn't have time for it, but thank you. Bye.
Thank you, Bindu.
Okay. Kicking off our next session is none other than, I don't know if Colin, you want to introduce Ganesh. I mean, I will say that I'm an IITB alumnus, so I'm very, very proud to have Ganesh here, but Colin, go for it.
Hi. Yes, I'm very excited to introduce our next speaker, Ganesh Ramakrishnan. He's currently an Institute Chair Professor at the Department of Computer Science and Engineering at IIT Bombay. His areas of research include human-assisted AI, AI in resource-constrained environments, learning with symbolic encoding and domain knowledge in machine learning, and other areas of efficiency in machine learning. Ganesh has received awards for his research, such as the IBM Faculty Awards and other awards from Qualcomm, Microsoft, as well as the IIT Bombay Impactful Research Award. And at Abacus, we've been very lucky to collaborate with Ganesh recently. And so I'm very excited to hear this talk. So Ganesh, please take it away.
Thanks, Colin, for a very generous introduction. Thanks for hosting this talk. I'm just going to screen share. Can you please confirm that you're able to see my screen?
Yes, we can see your screen.
Thanks. So I'll give a brief overview of a platform that myself and my colleague Rishabh Iyer at the University of Texas at Dallas have been building with a whole bunch of our students, both at IIT Bombay and at UT Dallas. The idea behind this platform is to make it possible for people in resource-constrained environments to be able to build models both in data efficient and compute efficient manner. So the talk is meant to present our open source toolkits, and you'll really like to encourage the audience here, the community at large, build upon our toolkits in two ways. Either you can integrate new algorithms, or we'll be very happy if you could use these toolkits in your applications. We're all aware that deep learning has achieved near human performance in multiple fields. There's a strong growth in the both in the complexity of the networks as well as the number of networks. And the issue then is, has deep learning been solved? Yes, deep learning has reached human performance in several tasks, but the problem is that you need large data sets and massive models. In addition, there could be issues of fragility owing to biases in the data. There could be massive label skew. In addition, the process of labeling data itself is very expensive. Just to give you an insight into the kind of cost incurred in the compute-intensive deep learning models, for example, to train a BERT model in Wikipedia and Book Corpora data set, you could incur 200,000 USD, whereas for a single deep model for NLP with network architecture search, you'd incur 237 million. I mean, this is INR Indian rupees, but $3.2 million. So you can also measure the impact in terms of carbon footprints. The other aspect is labeling cost. The labeling cost, of course, increases as you go from image to